industry standard on soldering, ANSI J Standard 001. In the first part of this videotape, we will continue to review the remaining dimensions for rectangular chip component solder joints, as specified in the Table 9-5 of the J Standard 001. But it's important to understand beforehand that you are not expected to measure every single dimension for every solder joint on the board. What then is the purpose of all of these dimensions and numbers? These dimensions are generally used to define the upper and lower statistical control limits for the component placement and soldering processes. This means that whenever you notice that your placement machine is positioning components beyond the acceptable limits that we will be explaining, then you need to make sure the process is corrected immediately. Prevention is the key, not rework. But what about rework? What should you do when you see a solder joint that doesn't meet the minimum size requirements? Do you leave it alone or touch it up? The general rule is to avoid rework whenever possible, since it is possible to damage the board during the rework process. In some cases, especially in Class 3 products, the entire assembly could be rejected for one solder joint that doesn't meet the requirements of the specification. In cases like this, you may have to rework the solder joint. Usually, however, on a Class 1 or 2 assembly with only one solder joint that is slightly less than the required minimum size, the leave it alone rule applies. But first, be sure that you communicate the problem to your supervisor to ensure that the source of the problem is corrected. Now, what if a Class 1 or 2 board has a solder joint that is way below the acceptable limits, so much that the joint is clearly too small to hold up during the mechanical stresses of day-to-day operation? In cases like this, you may also need to make a decision to rework the solder joint. Again, the decision to rework a specific connection is different for every board and every company. The dimensional requirements in the ANSI J Standard 001 provide you with information you need to help you make these important decisions. Your company's requirements may be slightly more or less stringent than the J Standard, and of course your company's workmanship standards will be the final criteria. But it is helpful to know what the industry standards are to gain some perspective on the relative importance of each type of deviation. Your job is to know what the current requirements should be for every assembly you build. In the first video in this series, we explain the maximum side overhang requirements from Table 9-5 of the J Standard 001. We represented the width of a rectangular termination by the letter W, and the width of the land by the letter P. We'll be using these same dimensions to evaluate the minimum end solder joint width for a 1, 3, and 5-face termination, since all of these different termination types have the same overhang and end joint width requirements. What we're trying to determine now is how wide the solder fillet has to be. We will call the minimum end joint width dimension C. Again, from Table 9-5, the minimum width of a solder fillet for Class 1 assemblies must be at least 1/2 the width of the component's terminations, 0.5 times W, or 1/2 the width of its land, 0.5 times P, whichever is the smaller dimension. As we said before, the component termination on a Class 1 assembly can overhang off of the land by as much as 1/2 of the width of the termination itself, or 1/2 the width of the land, which is also the same as 0.5 times W or P. This means that if a Class 1 component overhangs the land by half of its width, then the solder fillet will need to extend the full length of that part of the termination remaining on the top of the land. On Class 2 for commercial products, minimum end joint width requirements are the same as for Class 1. Class 3 assemblies, because of their higher reliability standards, require the minimum solder joint width to be at least 3/4 of the width of the land, or 3/4 of the width of the termination, whichever is smaller. All of these dimensions may be rather hard to remember, especially if your company builds assemblies for more than one class. It may be a good idea to keep a copy of the ANSI J Standard 001 on hand in order to refer to Table 9-5 whenever you have any questions. To further illustrate these soldering requirements, another IPC specification, the A-610, is a more visual guideline that makes a useful companion document. Most of the solder joint criteria from the J standard are graphically or photographically illustrated in the A610 manual. Your company may also have its own workmanship standards, or may wish to create a pictorial reference manual like the A-610. To help you with such a project, all of the images for each videotape in this series are available in separate slide sets for you to use to build your own reference document. The next dimension we need to evaluate is called the minimum end overlap, or dimension J. J indicates how much the termination is required to overlap or extend onto the land. Although there is no specific dimension called out, all three classes require some amount of end overlap. The minimum solder thickness, or dimension G, determines the minimum thickness of the solder in between the land and the termination. This is crucial because printed wiring boards will expand as they heat up during use. The lands will also move in the same direction that the board does, but the components may not expand quite as much as the board. The solder joints provide the flexible link between these two parts. If there is not enough solder to absorb the stress, the joint will crack and an electrical failure will be the final result. Although neither Class 1 or 2 assemblies have a specific dimensional requirement, they do require a properly wetted fillet, which means there must be a sufficient amount of solder between the termination and the land. Class 3 assemblies require at least 0.2 of a millimeter of solder between the termination and the land. Anything less is unacceptable. The next dimension we need to check is the minimum fillet height, or how high the solder fillet needs to extend up onto the termination. This is called dimension F. For all three classes of assemblies, the solder fillet is allowed to extend onto the top of the end cap metallization as the maximum fillet height. However, the solder must not extend onto the body of the component. The minimum fillet height in the Class 1 category calls for a properly wetted fillet of any height to be considered acceptable. Both Class 2 and Class 3 assemblies require a minimum fillet height of G plus 1/4 of dimension H. You may remember that G is the thickness of the solder underneath the component. Dimension H is the height of the termination. This means that the minimum fillet height needs to extend from the land upwards to the bottom of the termination, which is dimension G, and then further up at least 1/4 of the way onto the termination itself. For both Class 2 and 3 assemblies, there is also a minimum fillet height dimension of 0.5 millimeters. As long as the fillet meets the smaller of these two requirements, the joint would be considered acceptable. The final parameter we need to verify is the side solder fillet. In the first video, we discussed how rectangular chip components come with different styles of face metallization. Some come with one metallized face. Others have 2 or 3 faces, and some have terminations that wrap around all 5 of the end surfaces. Only the 5-face terminations can have side fillets, since there's no metal on the sides of any other termination style. Side fillet dimensions are not specified, since they may or may not add strength to the solder connection. There is no specific requirement called out in Table 9-5 for any of the 3 classes, although the solder should be properly wetted. This means that if a 5-face termination has less solder on one side than on the other, or is completely lacking a solder fillet on one side, it will still be acceptable for all 3 classes of assemblies. That's all of the dimensional requirements for rectangular components from Table 9-5 of the J Standard 001. Let's stop now to make sure that you understand what all of these numbers mean, and to discuss what you should do whenever you notice a solder joint that violates these dimensional requirements. In this next section, we'll be looking at many of the typical soldering problems that can occur on rectangular chip component solder joints. We'll also be discussing some of the potential causes for each of these imperfections or defects in order to give you a better understanding of the range of acceptable variations. The first, and possibly most common type of assembly problem, is component misalignment. One of the causes of misalignment is inaccurate placement during the automatic placement operation, especially when adhesive is used to temporarily stick the components onto the board. Now that you understand how to apply the dimensional requirements from Table 9-5, you can evaluate the acceptability of a misaligned chip component for all three classes of assemblies. Another condition that is relatively common is varying amounts of solder, from insufficient to excessive. In the previous videotape, we explained that the position or angle of the component termination as it passes through the solder wave can affect the shape of the solder fillets. If the components pass through the wave in a perpendicular direction, the leading edges will tend to be concave, and the trailing edge fillets will typically have a more convex shape. We also mentioned that the wave soldering process tends to produce solder fillets that are fuller than reflowed soldered connections, since the solder wave provides more available solder than from the limited amount of solder paste that is applied to the lands. The solderability, or ease of wetting of a termination, can also affect the contact angle of the solder. The more solderable the metal, the lower the contact angle should be. As long as the contact angle of any solder fillet is still less than 90 degrees on both the component termination and the land, then any surplus solder may be considered acceptable. Again, the dimensional requirements that are called out in Table 9-5 will define the acceptance criteria for the physical size of any solder joints, which must be met by both wave and reflow soldering methods. Remember that each solder fillet can have a different size and shape, as long as it meets the minimum requirements. Another cause of different sized solder joints is the relationship between the size and shape of the land pattern on the board to the size and shape of the component terminations. While a detailed discussion of land pattern geometries is beyond the scope of this videotape, if you would like more information on this subject, there is another IPC publication, SM-782, that provides recommended land pattern configurations for all types of surface mount components. Mismatched land pattern geometries can cause drawbridging or tombstoning, which are different degrees of lifting of one side of the component during reflow soldering. Drawbridging and tombstoning can also be caused by poor solderability of either the land or the termination on one side of the component. If one side of the component is more solderable than the other, then the surface tension on the more solderable side can lift the other end off its land. Different amounts of solder paste on the lands can also cause differences in solderability. Regardless of the cause, drawbridging and tombstoning are not acceptable conditions for any class of assembly. Solder webbing is a continuous film of solder covering any areas of the board where the solder is not supposed to be. Webbing can occur anywhere and is typically caused by either an uncured solder mask or by improper flux application during wave soldering. Normally, solder shouldn't stick to solder mask, but if the mask was improperly cured or if it's defective for some reason, then webbing can occur as the board is passed over the solder wave. Disturbed or cold joints are characterized by a dull and grainy appearance. This type of condition is usually indicative of contamination, improper cooling after soldering, or movement of the component during the cooling process. It's important to be able to differentiate between the grainy or dull appearance of a cold solder joint and the normal gray color and satin-like finish of a reflowed solder connection. Often it's difficult to tell the exact cause of a dull solder joint, but if there are only one or two discolored joints on the entire board, and all of the other attributes of these dull joints look good, the problem may be caused by a contaminated component termination or lead. Whenever you discover a problem such as cold solder joints, webbing, tombstoning, or any other defect that continues to occur, it's important to take immediate action so that the cause can be eliminated. Rapid feedback will help prevent the formation of additional defects. Another defect, solder bridging, can also occur around any type of surface mount solder joint. This may be even more of a problem on surface mount boards than on conventional through-hole assemblies, since the surface mount lands are usually located closer together. Bridging can be caused by an improper design of closely spaced conductors or lands, or from misadjustment of the wave soldering equipment. On reflow soldered boards, bridging can be caused by a number of solder paste material or paste printing parameters, or by the component placement process. The solder paste printing stencil or screen could be too thick, or the opening could be too big, or perhaps the solder paste may not meet the specific requirements. Solder bridges can also be caused by paste spreading out from excessive pressure during component placement. Any continuing problem of this nature should be reported immediately. Solder bridges definitely need to be fixed. The solder is usually removed with a solder removal braid or vacuum desoldering tool. Then the joints are resoldered with the correct amount of solder. Solder balls are another condition that can occur on the surface of the board. On wave soldered assemblies, solder balls are typically caused by an improperly cured solder mask or excessive pinholes within the cured solder mask. On reflowed assemblies, solder balls are typically caused by oxidation of the solder particles in the solder paste, or by improper baking of the paste prior to reflow. Solder balls can easily be dislodged by slight contact or even vibration. It is possible that a loose solder ball can become lodged between adjacent component leads or conductors and create an electrical malfunction. That's why it's necessary to remove any that might potentially come free within the assembly. If solder balls violate minimum conductor spacing requirements, then you have no choice. They have to be removed. The next condition is mounting adhesive on the lands, or inside the solder joints. This condition is only associated with components that are wave soldered, since there is usually no mounting adhesive used in the reflow process. This condition can be caused by excess adhesive that gets pushed onto the lands during the placement process, or because of old or defective adhesive that stretches out like a string rather than separating cleanly from the applicator nozzle. Adhesive inside the solder joint can reduce the size of the soldered area, leaving insufficient solder to provide a reliable connection. Therefore, this is an unacceptable condition for all three classes of assemblies according to the J standard 001. Now we'll look at some visible and not so visible imperfections in the solder joints. Voids, pinholes, pits, and blowholes. These conditions are typically created by the release of steam or solvent vapor during the reflow or wave soldering operation. Prior to the solder reflow operation, the assemblies may be baked in an oven to drive out any moisture or volatiles that are present in the solder paste. Pre-baking helps to minimize the formation of these imperfections. In wave soldered assemblies, the cause of these types of imperfections can generally be attributed to contamination of the component terminations or lands. Remember that the solder joint extends underneath the in-cap metallization. Anything underneath the component will be impossible to see without special equipment. X-rays are often used in referee cases to inspect underneath components and inside the solder joints. Here's an example of a solder joint that looks fine on the outside, but reveals some imperfections underneath the component that would be invisible to the naked eye. At this time, voids, pinholes, pits, and blowholes are not considered to be significant defects for any class of assembly, unless improper wetting is also evident. They may, however, be an indication that something is wrong in the production process and should be brought to the attention of your supervisor to correct any potential problems. Defects caused by improper adhesion of the solder are known as de-wetting and non-wetting. We covered de-wetting and non-wetting in the first tape in this series. You may remember that we described de-wetting as a pulling back of the solder from either the land or the component termination, almost like the solder decided against remaining where it was supposed to be. There are a number of potential causes for de-wetting: contamination, incorrect preheating, problems with the flux. But the most important consideration is how often the de-wetting occurs. If you find one de-wetted solder joint every once in a while, that's one thing. But if de-wetting occurs continually, then there's a serious problem that needs to be corrected. Non-wetting, or the complete lack of solder bonding to the land and termination, can have the same causes as de-wetting. It is sometimes hard to differentiate between non-wetting and de-wetting, especially if the lands on the board are tin-lead plated, or the component terminations are nickel plated, since both of these metals are the same color as solder. Non-wetting is relatively easy to detect if the surface to be soldered is copper, since the copper would be exposed. Non-wetting is considered a serious defect if it interferes with other dimensional requirements of a solder joint. As with de-wetted joints, a repeated occurrence is a warning that something has gone wrong in the production process. It must be reported and corrected as soon as possible. That covers all of the solder joint requirements from the J standard 001, and all of the major defects for rectangular chip components. While surface mount design and assembly is considered a mature and mainstream technology, acceptance criteria for surface mounting will continue to be updated and reviewed as the technology evolves. One way to keep up with technological innovation is through participation in IPC meetings, whether in the working groups that develop the surface mount standards, or in the technical sessions that report on the latest developments from around the world. This concludes part 2 of the series on surface mount solder joint evaluation. In the next video, we will be explaining the acceptance criteria for cylindrical and bottom-only chip components.